So let's get to it. I'm not going to talk very much about why one might think that there is a problem. Most of the talk will be on different possible ways of addressing it, but let me just, by way of introduction, stating some of the background assumptions here, something about the general picture that is underlying this kind of effort. So you're all familiar with this idea of the possibility of some kind of intelligence explosion at some point, maybe, when machines become sufficiently clever, attain sufficient general intelligence, maybe they can apply that to enhance their own intelligence even further. Now, just to say one thing here, one needs to sharply distinguish the question of how far away into the future such a hypothetical event is from the question of if and when such an event ever happens, how quickly does it unfold? How soon could you get from, say, human level engineering intelligence to some form of super intelligence? Now, and I'm not going to argue for this either, this is just kind of background, that one might then think that a true machine superintelligence would have a range of superpowers, that it would have radically superhuman abilities in a number of different fields, including especially intelligence amplification, the ability to further increase the intelligence of some system by doing computer science or neuroscience research or inventing faster hardware or whatever, but also a range of other ones that might contribute to such a system becoming very powerful and able to shape the future. And you can conceive of some kind of scenario where initially there is background research in relevant fields like computer science and machine learning, and at some point perhaps some kind of simple system is created that has the ability to self-improve. It initially uses this intelligence amplification ability that it has to attain whatever other superpowers it doesn't have from the outset. And then when it has sufficiently strong powers, in one of these scenarios, you could then imagine that it would seize control over things. It might eliminate humans, it might then initiate whatever process it deems valuable. It might reformat the resources it can get its hand on into whatever structure maximizes values according to the AI's own utility function. So we don't have to assume that any of that is true, but for the purposes of thinking about safety, it's productive, in my view, to focus on, as it were, the worst case. And so we want to make a number of conservative assumptions here. And conservative in this context doesn't mean those that we can be almost certainly sure are true. Conservative here means that if we want to make sure that the AI is safe, that we have some reasonable ground for being confident that nothing will go wrong, then we will assume that the AI is very powerful and that this happens very quickly, and that there are a number of other of these factors that make it harder for us to solve the safety problem. It's interesting that this happens there. So one conservative assumption is that this takeoff is fast, and that the AI gets the panoply of superpowers just alluded to. Another kind of related to this is that if the AI were to be released into the world, given access to actuators so that it could roam around freely, that it could then form a singleton, that is, it could take over the world. It could form a world order where it is at the top and decides what happens. Another is that if we can sort of vaguely see how something might conceivably be done, then the superintelligence can do it. So it might be able to achieve a lot of things, unless we can show that they are incompatible with the laws of physics, or unless we can provide a very clear and compelling case for why even a superintelligence could not do it. Then the safer assumption is to assume that it might be able to do it. And the AI is not less shrewd and sort of tactical than the cleverest human would be. So if there is some, if we rely on the idea that the AI would pursue some plan that already we can see how the plan would fail, then we have failed to heed this conservative assumption. We have not granted the AI enough. Another conservative assumption is that human values are complex and fragile, that it's difficult to capture whatever it is that we think is necessary for the world to be a good place. So if we want to make an assertive assumption that a freely roaming superintelligence that does not have human value would cause an existential catastrophe. We should also bear in mind that human users sometimes act unwisely, and that some safety measures might fail for reasons we do not anticipate. This is terra incognita. The first time we actually develop a superintelligence, we will presumably not have thought of everything that could go wrong. So this is kind of what creates the problem. If one wants to try to plot the path forward that gives some reasonable reassurance of success, even in the light of these conservative assumptions, then one has this major challenge, which we can call the control problem. How to make sure that we can control the outcome of an intelligence explosion to achieve something that is, by human lights, valuable. There are two agency problems that one can distinguish. So one is the ordinary one, where you have some sponsor who wants to commission the creation of a superintelligence, maybe appoint some team. This could be a government or a research council or whatever. They then have to trust these people who are implementing it that they will do what they are supposed to do. So this is a familiar kind of principle-agent problem. It occurs all around the economy. People have different management sciences, different ways of dealing with this. It occurs mainly in the developmental phase, during the programming and creation of the superintelligence, not after. But it's the second principle-agent problem that I will focus on today, which is this control problem. Like, how could a human control what the superintelligence will do? How could a project that builds the system control what the system will do even after it becomes much smarter and potentially more powerful than the system itself? So this occurs mainly in the operational phase, like once the AI has actually been built. How do you then control it? Although also in the actual bootstrap phase. And here, ordinary management techniques do not straightforwardly apply. Here some new insights are needed. So that's all by means of sort of setting up the problem. Now, there are two broad classes of approaches to this control problem that we can distinguish. The first of this is capability control. So this is when you try to ensure a safe outcome by limiting what the AI is able to do. So you limit its powers, you constrain it, you clip its wings in some way. The other big class of control methods is what we might call motivation selection. So here the idea is that you try to shape the AI's motivations such that even if it could destroy the world or cause enormous harm, it would choose not to do it because it wouldn't want to do that. These also might be used in combinations, but these kind of define two very different ways of thinking about this problem, both of which I think are very worth pursuing. So the rest of the talk will basically be going through these in some detail. We'll start with the capability control problem, so we'll hopefully get through at least that, then we'll see. We might not get through all of what there is to say about motivation selection, but we'll see how far we get. Okay, so capability control. What methods could we apply to try to limit the ability of an AI to cause harm, as given these conservative assumptions that the AI becomes super intelligent and has superpowers? So here is an initial list. The first, we have what we might call boxing methods. The idea of trying to constrain the AI so that it's limited to, say, a box. And this comes in two versions. You can have some kind of physical containment and what we might call informational containment. These are not sharply distinct. But so instead of having an AI that has access to actuators and can control robots and make telephones around the world or go onto the internet, you could imagine having a box, say a freestanding computer with no internet access. If you want to be paranoid, you could put the whole thing in a Faraday cage, and it would make it really difficult for the AI inside the box to affect directly by any physical means the external world. So this would be kind of physical confinement. Informational confinement would be, well, you still need something to come out from the box, like, because if you completely isolated the system and just let it run on itself, then maybe it would be safe, but it also wouldn't be very useful. So informational confinement is the AI is allowed some kind of communications channel with the human operators, but the informational containment would limit or put bounds on what kind of information is allowed in or out. So maybe rather than being able to present things in graphics on a big high-resolution display, maybe it could only output a few bits or something like that. Now, the problem with these boxing methods is that humans are not secure systems. So even if we could be sure that there is no sneaky way for the AI to sort of generate electromagnetic waves by reshuffling electrons in a clever way that could sort of bypass the Faraday cage and then somehow use that to hack surrounding electronics, there is still this weak link in the chain, which is the human operator. So it's not conservative to assume that having a superintelligence being able to communicate you would not create a risk by it being able to figure out some way to manipulate you to do its bidding. It also doesn't prevent what we might call mind camps. So these are harmful effects that could occur inside the computer system itself. So if we have a superintelligence, it might create internally simulations of sentient beings, other kinds of digital minds inside itself, which could be mistreated. And so there's a possibility of harm and suffering occurring inside the box, which is not prevented by sort of encapsulating the box. This is not to say that boxing methods are useless. They might be used, but one shouldn't rely on them on their own. They might be useful supplements to other ways of trying to solve this control problem. So let's look at the incentive methods here. So the idea here would be that we would try to create incentives for the AI to behave well. I mean, after all, the world is replete with all kinds of selfish and nasty and psychopathic human beings, and they don't always run amok and go on killing sprees, although they sometimes do. So the idea here might be, could we use something similar to ensure that the superintelligence would not cause a lot of harm? So one version of this would be just to rely on general social integration. So if you release an AI, even a powerful AI, well, it's out there in a big, powerful world. There are a lot of other powerful agencies there that might keep it in check. Now, this is not a conservative assumption. The conservative assumption would be that the takeoff is very rapid, so that you might go from something that is human level to something that is radically super intelligent in a fairly brief period of time, in which case there might only be one of these. Like if this transition occurs over 1 week, it's not likely that there will be several different research groups that are simultaneously achieving this kind of takeoff. And also, if it achieves very strong superintelligence, it might be stronger than all the other kinds of agencies that existed. So one couldn't rely on the rest of the world being strong enough to constrain it using incentive methods. Another version of this is to deliberately engineer the AI. And this kind of involves a form of motivation selection, but a very simple one. Such that it would be motivated to want some particular reward signal, and then humans could have control over this reward button, as it were. And that might give us additional leverage. One has to be careful about how one would implement such a thing, though. One risk here is the wiring. So if it wants some kind of subjective reward signal that's like an electrical cable going into the digital equivalent of its pleasure center, and it really wants the signal to continue to come in, once it gets sufficiently capable, it can figure out that there is another way of making sure that its reward center is maxed out. It doesn't need the external cable, it can just activate its reward center directly. We have to assume that it has control over its own source code, its own mind, if we want to be conservative. You could define a different kind of reward button where the reward would consist of some event in the external world occurring. For example, if you had the ability to make the AI have preferences concerning some external object, you could create a little button somewhere in a bunker, and the AI would want this button to be pressed. And it wouldn't even matter whether the button was hooked up to anything. You could have a little Play-Doh button, and as long as the AI had beliefs about it, it might then want to behave in such a way that the people in the bunker who are controlling the button would keep pressing this Play-Doh button so that the AI would achieve its goal. But again, one has to be very cautious with this kind of method, in as much as there is risk that a sufficiently clever AI would figure out a way of seizing control over this Play-Doh button. Like it might initially play along, but surreptitiously develop some form of nanomolecular actuator that could infiltrate the human operator, or somehow come up with a scheme that would enable it to seize the control button and then achieve far more reward than it could by just kind of doing the human's bidding. And there are more clever versions of the same idea, but fundamentally they are possibly vulnerable to the same thing. So instead of having an actual reward button, you might have some kind of cryptographic scheme where the AI's motivation system is set up in such a way that it wants the solutions to various ciphers, and we keep sending it keys. And the keys could be stored, say, far away on the space shuttle or whatever, but there's still this risk that we might be outwitted. Also, the actual reward schedule would require careful design. Like, you don't want sort of reward to be maximized after a certain period of time, so that then it doesn't matter what the AI does. Or to have the discount being too steep, so that the AI doesn't care about the far future and just sort of take some desperate action to try to see. Or if the reward, if you have some kind of discounted reward and it's defined in terms of some time that elapses. If you're not careful about how you define the time, if you define the time, say, as what happens when a certain clock moves forward, which would be the most obvious way of doing it, once it actually operationalized time, then the AI would have an incentive to seize control of this clock to stop the discount from occurring. So all these kind of complications once you start to think through what this would involve. Stunting is the idea that we might somehow limit the AI's cognitive development in certain ways, so that it would have superintelligence in particular directions, but lack some other abilities that would be essential for it if it wanted to scheme to take over the world. Oh yeah, and one more thing about the reward button, that also doesn't prevent Minecraft. I'm not going to talk about the anthropic capture thing here. So this kind of idea of limiting the AI's intellectual development, there's a dilemma there, which is that either you cut down its intellectual development a lot, maybe then it's safe, but it also limits what the AI can do, so it limits its usefulness. Or if you allow it to develop quite a lot, then it's non-conservative to assume that even this system that has sort of progressed quite far beyond normal human engineering abilities and planning abilities and search abilities, that even that would necessarily be safe. That would be an non-conservative assumption. So you might be using stunting in some form during the developmental phase to sort of control the speed at which your system progresses, but sort of ultimately it seems that it would be unwise to rely on this to solve the control problem. And finally here we have tripwires, which we can define as sort of automatic monitoring mechanisms that are set up to see what the system is doing, such that if it detects some kind of prescribed activity, it immediately shuts the system down. So it differs from incentive methods in that tripwires don't presuppose that the system is actually aware of the existence of this. So for an incentive to work, the system must know that it's being incentivized. But the tripwires might work with or without the system's knowledge. So let's look at some examples of that. An obvious one would be during the developmental phase of the project to institute some form of automated capability testing, where you want a controlled takeoff. You don't want something that suddenly, while you're away on your lunch break, kind of undergoes the singularity. You want something that you could maybe take small steps and check it very carefully at each step. So one way of doing this, if you were doing experiments involving recursive self-improvement or really pushing the frontier in machine learning and research, would be to implement a process that continuously measures the system's performance. And if either the rate of improvement suddenly becomes unexpectedly high, or it reaches some very high level of absolute capability, then to put the breakdown and call in the programmer so you can review what's going on there. You need some kind of capability measure to do this, and for example, as an absolute capability, if it were sufficiently smart to develop without it being programmed in from the beginning, like a relatively sophisticated theory of mind where it could conceive of other agents, if that suddenly emerges out of your complex processes, maybe that would be a sign that it's time to pause and stop. You could have a number of sort of IQ-like measures of different types. It would be wise probably to use some disjunctive metrics. You don't have to pick one. You could just throw a number of different things and say that if it succeeds to a remarkable degree on either of these different kinds of tests, that should light a warning signal, and it's a signal that we should pause the system and think before we take the next step. And another type of tripwire would be to create honeypots, tempting resources that the system is not supposed to grab, but they are there, apparently, and then we could monitor it, and if it does actually try to grab them, then that's a sign that something has gone wrong. So we don't want to actually have the system have access to the internet, but you could sort of have a USB cable plugged in, except it doesn't lead to the internet, it leads to this kind of automatic shutdown switch. So if the system actually tries to access the internet through this channel, then it gets shut down. Another thing that would be useful for these kinds of advanced experimentation would be to have a flight recorder, which is like some kind of way of continuously recording everything that is going on in the system and all the inputs with exact timestamps and run seeds, so that you could, if you wanted to, recreate what has happened. And ideally, that this should be inspected routinely, either by some kind of other independent software or by a human. And then this obviously depends on exactly what the system, what type of system it is, what the architecture is, how transparent it would be to this kind of inspection. But with some very advanced type of system, at least of a certain kind of architecture, it's possible that it would have something analogous to an internal dialogue, like humans often. If we are making plans, we could sort of have these, you can almost hear inside our own minds like this little voice that is planning out the different possibilities. If somebody were monitoring us in that way, you could imagine that even without understanding completely how our brain works, they might be able to sort of pick up what is going on in our auditory cortex and transcribe that into words. So for some kinds of systems, something similar might be possible, and that would be one way of organizing that. And then, in general, if you were designing this kind of advanced system and you had certain expectations based on your understanding of the system, how it should behave and how it should not behave, it would be good practice to install tripwires around those expectations. So you make as many. You think you understand your system, otherwise you shouldn't be doing this at all. And then encode your expectations in tripwires such that if any of those expectations is violated, it shuts the system down and you have a chance to review what's going on. And the more of those, the merrier. Now, one big limitation of tripwires is that they are only as effective as the human response. Even if they all work as intended, the best that happens is that the system is shut down. But then what happens? And so you have this team that have been working for many years maybe, and frustrated, and finally they're starting making progress and the system is actually improving itself, and then a tripwire is triggered. Now there's going to be a huge temptation at that stage to patch over whatever it was that triggered the tripwire, or remove it altogether and proceed. Like that's just, there's going to be this immense psychological pressures to do that. So tripwires are somewhat non-conservative in that it's possible that the system might kind of figure out ways of anticipating the existence of tripwires and then adjusting its behavior before it actually triggers one. It requires discipline by the human programmers to actually do something constructive and meaningful in response when a tripwire is triggered. You actually need to maybe redesign the system. You need at least to understand exactly why the tripwire was triggered and make sure that you know why that is. And not sort of just try to persuade yourself that you figured it out and proceed. And again, it doesn't prevent mindcrime. So to summarize this first section of the talk about the capability control measures, for all types of systems in the developmental phase, it would make sense. All kinds of systems that purport or try to become artificial general intelligence, so that really pushing the frontiers of inductive programming or self-improvement, like all this kind of really cutting edge, have physical containment, like don't give it an internet port, just keep it physical outside of it. It's very easy to do. If you want to be able to read Wikipedia, like just store a copy of Wikipedia and install that in its memory rather than enable it to read it. Use stunting, that is controlled capability growth, to kind of moderate the rate of improvement in case something should succeed more than you thought. And use tripwires. Those are only useful for the developmental phase. Now once you have an operational phase, like once the system is kind of full-fledged, then the following kinds of capability control measures might be applied, but only for Oracle class systems. That is, only for systems that are intended to serve as question answering systems. Not for systems that are intended to be out there in the world directly controlling actuators. But you might, for these kinds of Oracle systems, use informational containment, physical containment. You might consider some kind of incentive methods, and you might continue to use tripwires for these super intelligent oracles. And again, there's this further issue of anthropic capture, which it'll take too long to get into, but the idea there is that the AI might be unsure whether it's whether it's like inhabiting a simulated reality or not, and you might try to encourage that by different means, and that raises another set of issues. But let's press on. So now, let's get to the second type of possible control methods. Motivation selection. So one way of trying to do this would be to start with a system that already contains the kinds of motivations you want, say a human, and then augment that system to make it super intelligent. Now, this obviously is relevant for a certain kind of approach to super intelligence, like whole brain emulation, where we might actually start off with a system that is human-like and then build intelligence on top of it. You might hope to do this in a way that it inherits the motivations. And you could, in principle, end up with a super intelligence with human motivations through inheritance, as it were. Or if you could sort of biologically enhance the intelligence of a human being or something like that, maybe you could achieve human-like motivations through augmentation. But we will not be focusing much on that avenue to superintelligence. We'll more be thinking about the case of artificial intelligence. Then there is a possibility of some form of direct specification, where you like explicitly program directly what kinds of goals and values you want it to have. There's a possibility of, rather than trying to encode the full panoply of human values that you want the AI to pursue, you encode something that would make it want to limit its impact or effects on the world, some form of domesticity motivation. It wants to remain in the box. It wants to not hack its way out of the box by manipulating the human gatekeepers. And finally, the idea of trying to encode some human-like values, but not by directly specifying them in full detail, but by motivating the AI to pursue some process that will lead it to discover what human values are, and then to try to maximize those values. So kind of indirect specification of human values. So these problems, these approaches that face this value loading problem, which like how do you actually get human values into the AI? Now remember that one of the conservative assumptions we made was that human values are complex and fragile. The direct specification here doesn't seem promising. I mean, even like, say like so, suppose like love is one of those things that the world should contain in the future in order for it to like be a really true success story. Now, how do you actually type in C++ like the definition of love? I mean,
make love.
Sorry?
Make love.
So you have some difficulties there. Now, it's possible that with a more simple goal, like some form of domesticity, maybe you can directly specify it. But otherwise, you face this value loading problem. So here is a number of possible ways that one might think of approaching this. So explicit representation, that's just one I mentioned, it's like, looks hard. The more complex and fragile human values are, the less possible it is that we can directly program it in and get it right on the first try. Another would be some kind of evolutionary selection. So the idea is to generate a lot of little systems, processes, and kind of select these on the basis of how they behave. So maybe you create a little toy world. You want systems that are cooperative and sort of select the ones that cooperate on the first round in your toy world, and you generate more. You could keep going like that. There are several problems with that. One is that that you have the possibility of any perverse instantiation, which is the idea that there might be ways of meeting the selection criteria in your simulation, such that you say you cooperate under these conditions where you think you might be in a simulation or in an evolutionary selection process, but you cease to cooperate once you are in a different context. And in general, there might be ways of, so you have some sort of formal criteria, fitness functions, to run your evolutionary selection process, and unless that fitness function completely and accurately captures what we really value, then there is this risk that the AI, once it's released from the box and grows sufficiently in intelligence, will find a new way of realizing the values that it has acquired, those defined by the fitness function, but that don't match human values anymore. reinforcement learning might be an easier case to illustrate this. So you might want the AI to make people happy, and you give it a reward whenever there's some sort of smiley user face that is beaming at it because it has done something pleasing. And, now one risk here is that if, depending on how you set up the reward mechanism, it might just create the wire-heading fallacy, that once it becomes powerful enough to achieve more reward by wire-heading itself, it will do that instead of seeking to please the user. But suppose that you manage actually to incorporate the value of sort of smiling humans rather than the reward signal that it gets from that. Well, then it might initially produce smiling humans by being pleasing, but later on it might figure that there's a different way of producing smiley humans by sort of creating cutouts of humans, or by implanting electrodes in their facial muscles, or by other ways of perversely instantiating the goal of smiling humans. Also, these don't protect against mind crime. In fact, rather the opposite, like evolutionary processes kind of requires a huge number of variations of superintelligence-like structures to occur, and that is almost a recipe for mind crime. And also that it's intrinsically dangerous. Like if you're actually going to select among a population of superintelligent like agents, you have to run all of these, and they themselves might place a danger even during this selection phase. Like they might break out or figure out some other way of gaming the system. Another is this notion of value and cliché. So this maybe, well, let's stop and think about how do we humans acquire our human values. So not everything can be genetically encoded. Like which particular person you happen to love obviously depends on whom you met and your experiences with that. It's not, there's not like big sort of global population registry encoded in your genome. So what our genes can do is at most create certain structures and predispositions to acquire different values, but in light of experience. So we accrete new final values depending on our experiences with the world. And one might think that one could use a similar method to have the AI accrete values. So you create some sort of disposition to acquire value as a result of your interactions in the world. Now, this remains something that should be researched further, but at the moment it's very poorly understood. It's not sufficient just to create a system that acquires values somehow. It needs to acquire values in exactly the same ways that humans do. It needs to generalize from its experiences in the same way that humans do, or in a very similar way. Otherwise, it might acquire values that diverge from our values radically when it is moved to a new context, from the kind of testing context or learning context, when the AI is weak and human level or unable to impose its will. And then once you move it to a different context, this divergence between the values it has accreted and the values normal humans would have accreted will manifest itself in an undesirable way. Motivational scaffolding is the idea that you could give it an initial set of preliminary goals and then allow it to develop cognitively to a certain level, roughly maybe a human level, at which point it might have developed human level concepts. So at some point, if you have some general intelligence, it should understand what love is, just as a human does, by sort of being able to interact with people who speak English and read novels and all of that. And once you have that concept in there, a representation of love in the AI, then maybe you could sort of freeze the AI and then rejig it, use some of those internal representations in the AI, move them into its motivation system and link things up such that it would then be motivated to pursue these human values and understanding these human values in the same way that we do. This also is probably worthy of further research, but at the moment remains poorly understood exactly how you do this. It also has the risk of encouraging procrastination, the lackadaisical approach to safety, in as much as if you really thought that motivational scaffolding was the way to go, you would be tempted to postpone working on the control problem, because you couldn't really do much anyway until you had an AI with human representations inside it. So you might just kind of kick the can down the road and say that, well, once our AI becomes human level, then we'll worry about it, then we'll figure out how to use these internal representations to build some kind of human motivation system inside it. So even if one did think that this was the way to go, one should then probably work on all the other approaches in the meantime, not to sort of then be surprised if this doesn't work. Value learning is also poorly understood, but here we have at least some leads, which I will not go into in detail, but maybe just say a few words. So within this kind of AI XI system, these are different optimality notions. So there are kind of two tests. You can define what you ideally would want your AI to do, like what's the criterion for optimal rationality. And then when you actually do AI, you would then try to figure out ways of approximating this in some computationally tractable way. And that's where most of the hard work is, almost all of the hard work. But there is still a little bit of hard work in defining clearly the optimality notions, like what is the thing that you're trying to approximate. And so the AIXI system, I think which most of you have heard of, is a kind of an attempt to formalize one optimality notion for a reward learning system using Solomonov induction. And we don't need to get bogged down here, but there are some generalizations of this. So in Marcus Hutter's AIXI system, it's a reward learning system, so it suffers from these problems that I alluded to earlier with reward learning, is that it would seem to succumb to the wire heading syndrome, that once it becomes sufficiently smart, it figures that it can maximize its rewards by removing all the humans that we're supposed to be rewarding with, and then sort of optimize the world to directly feed in reward signals. So rather than having the value being sort of to maximize some discounted future reward stream, you could try to have it defined in terms of possible worlds and a utility function that assigns utilities to possible worlds. And that's this sort of observation utility maximizer there. Daniel Dewey, who's in the audience, has done a nice paper on this, which I think is on display on the table outside. So those who are curious, you can look at that later. But that still has the problem of how you define the utility function. And this, like, explicitly coding this utility function is just this problem mentioned before. Like, if human values are complex and trivial, it's hopeless to think that we could just explicitly write out the utility function. So then the idea is that maybe we could create a system that can learn a utility function. And this is the bottom line here. What it would maximize is the expected utility, but where the expected utility is itself a kind of expected meta-utility. So there are several different possible utility functions. It doesn't know which one is the correct one. It has some probability function over that. And at each point in time, the agent would act to maximize the expectation of that. Am I running out of time?
Yeah, pretty much. Take a few more minutes.
How many more minutes?
No longer than the singularity. Preferably around 5 minutes.
5 minutes? Okay. Yeah, that's fine. So just to say that here, you can have uncertainty over which utility function it is that you want to maximize. However, you still need to define some criterion here for what it means for a utility function to be a correct utility function. Now, that might be easier than directly coding the complete utility function, but it's still a very non-trivial problem. Also, you've got to define this probability function such that it defines the probability of a utility function satisfying this correctness criterion given that we are living in a certain possible world. So that's also a very non-trivial way, but there might be clever ways, and there are some ideas, in fact, for how to do this, that these are not fully developed ways, and they probably wouldn't work in their current form, but there are at least some starting points for thinking about this. There's the sort of the Hail Mary idea, which we can talk about later maybe, and Paul Cristiano has some ideas as well. So we haven't solved this idea of the validator, but there are some ideas at least that one can start sort of pulling on. Institution design, the idea that you might create several intelligent systems, and then by arranging them in some kind of institutional architecture, you might have a system of checks and balances that could make them safe in some way. Carl Schulman, I think, in the second part of our conference, the AGI Impact, will talk about some things related to that. And then if you had this whole brain emulation system, then there are different kinds of validating techniques you might have to try to select the humans who are uploaded and then tweak their motivation. But that's also a topic for a different discussion. So in summary, and this summarizes the second part of the talk, that is the motivation selection part. We summarized the capability control part earlier. Explicit representation seems probably infeasible, except if what you want to do is not to capture human values generally, but to capture some much simpler goal, such as some form of domesticity motivation or wanting to answer questions accurately. It's an open question whether it might be possible through some clever way of directly representing such a simpler goal, and that might be relevant if what you're trying to build is an oracle, but obviously not for a genie. Evolutionary selection and reinforcement learning seem to be suffering from these fundamental problems that would make it unconservative to assume that they would be safe. So they look less promising, although in reality probably all avenues should still, in the ideal world, be pursued further. Value accretion and motivational scaffolding might hold promise. They have hardly been explored at all in this context, as far as I'm aware. More research is needed there. Value learning, more research is also needed there, but there's at least some interesting ideas to start working on. And then institution design, mainly relevant for whole brain emulation, but it might also be that some of those techniques could be applied to AI, but we don't yet understand it very well. And tweaking whole brain emulation through the equivalent of digital drugs and stuff like that seems mostly to be of interest for the whole brain emulation path, but not for the AI path. So the take-home message is that if we are convinced that there is this problem, we can distinguish these two broad classes of approaches to it. There are some ideas under each of these, some which we can look, say, are less promising, and some which look worthy of further research. But no methods have yet come anywhere close to providing a solution to the control problem that we could be confident to work even under these conservative assumptions. Thank you.
Okay, thank you. Questions?
Hey, one thing I felt a little bit uncomfortable about listening.
Could you introduce yourself, please?
Hi, my name is Fergal Reid. I'm a PhD student in sort of a machine learning area. And one thing I found a little bit uncomfortable listening to in the start of your talk was you talked a lot about what could be construed as methods to enslave a sentient being, you know? And there might be sort of an ethical dimension to thinking about that or planning that. And I'm sure you think about things like that. I'd just like to hear what your reaction to that is.
Yeah, I mean, it could be a topic in its own right. I guess there's several things to be said about it. One is that it seems less pressing than, so it's like possibly one entity whose welfare is on the line for a very limited period of time. After we're safely through this, then you might be able to sort of release this superintelligence, and it could have a very long future. So although there might be significant ethical issues, I mean, it relates to mind crime, which is kind of, so the AI itself is a special instance. If the AI itself suffers inside the box, it's a kind of a particular instance of sort of something gone wrong inside the box of mind crime. The distinction between the AI itself and the processes it chooses to create is also kind of arbitrary. Like, if it runs simulations, detailed simulations of other possible agents inside its own mind, if it thinks about them in such detail that the thoughts themselves are conscious in their own right, is that part of the AI, or is that like separate life that the AI is created inside the box? I'm not sure there is a clear distinction there, but in general that would be these issues. I mean, another thing to be said is that there is no necessary no strong ground for thinking that the AI would have to be suffering there. I mean, in a sense, the AI would be imprisoned in its box, but the box might be very wide. It might contain this virtual reality that is very expansive. I mean, we are imprisoned in the real world in the sense we can't get out of it, but we don't seem to think that that's a problem. And similarly, the AI might be confined in its virtual reality, but it doesn't necessarily mean that it would sort of be pacing up and down its cell and kind of longing when they're looking out at the tint of blue sky.
Maybe to drive the point of that question down a little bit more, it is entirely conceivable that that AGI we are talking about is actually a human mind that has been extended or transcended and augmented until it became, so to speak, superhuman in its capabilities. And I think this does raise the ethical issue. I mean, what would you do to this future super Nick Bostrom if he is confined to his box and his intentions are manipulated by the system and his capabilities are constrained. Isn't there also a need for perspective taking from the point of view of the other species, so to speak?
Well, Nick Bostrom is already friendly, so he could be let out immediately. And be allowed to form a single contract.
Manipulation.
To the extent that the motivation selection method works, and we can reliably tell that it works, then there is no need for any of these capability control measures. So in a sense, the motivation selection is clearly the ideal solution. Like, it's better to have a system that doesn't want to do harm than to have a system that wants to do harm but is kind of fettered up so it can't. Like, that's clearly not the best way.
But humans are harmful. We are doing great harm to the ecosystem, to all other species, and so on.
To ourselves.
Yes? Yes.
Yeah, so hopefully one can aim for something better, better than that, in as much as human values doesn't necessarily mean capturing all the things that individual humans actually want, but something that would have as its goal to realize that which we would accord value to. I mean, and there's like a whole separate talk about what those like suitable targets would be, like coherent extrapolated collision, there's like do what's rather right, there are like a number of these ideas for that.
Hi, Connor Shanky. I just wanted to ask a question about the very first slide, and it's you have a graph there, which is very similar to what other people talk about in the kind of the AGI space, which is this sort of gradual transition from something that is not comparable to a human being in terms of its intelligence, and then it gets very close, and then we go on the other side. But I guess the thing that I don't totally, in terms of this model of things, it seems that if you look at today, 2012, a lot of the artificial intelligences they're narrow intelligences in terms of their capabilities, like Google in terms of information retrieval, or say for instance something like Watson. But they're already in that narrow domain. They're superhuman in their capabilities, in terms of that specific capability. So it seems that if things continue, you're going to have an aggregation of superhuman capabilities that are going to superhuman intelligent capabilities that are ultimately going to collectively come together in such a way that you're ultimately going to have something that has an AGI type of capability, but right off the bat, it's already going to be something that's completely beyond what an individual human being is from an intelligence perspective. So just in terms of the idea or the model of how we're approaching this, is this indicative of really what's happening or what could happen?
I'll say it focuses on one particular class of scenarios where you had this one entity that became very powerful. Now there are other important scenarios. One is, and I think maybe, I don't know if Robin Hansen is here, he might talk about that later. I think he's giving us one later. So in a multipolar outcome where you have many different kind of agents and that exist in some kind of economy and are competing, that has its own kind of risks, but it's a very different set of challenges here. So part of the answer is just that for the purpose of this talk, I focus on this class of scenarios. Now there's a little bit more to be said, which is that although there are various kinds of risks and issues arising from individual, like narrow domain superintelligences, like privacy and all these kind of things, I think there's a distinct set of issues that arise only when you have a system that has sort of superintelligence that includes the ability to plan and scheme and for general purposes. And these domain-specific superintelligences, there's kind of one particular domain-specific skill that's different from the others, which is, say, the first one here, the intelligence amplification superpower. In as much as once you have a sufficient capability in that domain, you can have all the other domain-specific abilities as well. Like once you have a sort of radically superhuman ability to design different kinds of cognitive modules, for example, then even if you didn't initially have any appreciation for poetry, if you had like a superhuman ability to design cognitive modules, you could design a poetry appreciation module or a kind of search module or a robotics navigation module or whatever else. So there's one of these that once you have sufficiently much, it kind of generalizes, and you might then use this one super ability in computer science research, as it were, to acquire all the other that you don't have. So it might be that you have a lot of domain-specific systems up to a certain point of development, but once the intelligence amplification system module becomes sufficiently strong, then you get a kind of universal intelligence that is able to extend itself in arbitrary direction.
So I'd like to ask about the concept of an oracle as opposed to an AGI that has direct control over things. How much do you distinguish those two things? Because let's say that the questions you ask of an oracle are not completely irrelevant and useless, but actually relate to things that you want to then apply, so then the answer of the oracle becomes something that you then use in the real world. In a sense, isn't it just a system that does have some control in the real world, but there is a human communicator in between?
Yeah, so the distinction is not clear-cut. Now, it's possible that some types of oracle systems might be designed such that their only goal, say, is to provide accurate answers to yes/no questions using no more than a limited set of computational cycles and with other various constraints. Which would be different from the kind of system you wanted to release into the external world, where you'd need a much more complex goal. So there's a set of control methods that could be applicable to Oracle that just wouldn't be applicable in the first place to a sovereign system that is meant to be. If you want a system that roams the world and controls everything, you couldn't keep it in a box without communication channels out. It just kind of would be a different goal to work on. But certainly the fact that humans are actuators that the Oracle has access to is exactly this issue, which human systems are insecure. So that's like the biggest problem with relying on boxing as a way to solve the control problem. In defense of these boxing methods, it's perhaps the only control method that we could implement right now and have a chance of working, or with like 2 weeks worth of work. I mean, you could actually you could certainly just disconnect the Ethernet cable. You could create some of these other tripwires with a few weeks of research, and it's a very practical thing we could do now. Whereas, say, these value learning motivation selection techniques are open-ended research programs that we hope will bear fruit, but it might take years or decades before we could actually really implement them.
Okay, I think in the interest of time, the remaining questions have to be discussed in private. So I want to thank the speaker for these.